Welcome to Digital Electronics. In this lesson, we're going to be learning how the logic design process works. Now we know about AND gates, OR gates, and inverters known as the AOI logic gates, but we haven't learned how to use them to implement to solve a circuit. As you can see on my screen, I have a weird cycle, like a tandem cycle that has two seats. I want to point out that the front part of the cycle has only a place for the user to rest their feet, but they're the ones that are in charge of steering the cycle. In the back seat is the part that is actually propelling the cycle forward, but they cannot steer the cycle than the person in the back. Okay, so this is the story that I'm going to use to show you the logic design process as following one example. So in this example, for this cycle, we have three friends, which is Amy, Ben, and Charlie. So Amy, Ben, and Charlie are friends, and they buy this cycle. And they want to make a circuit that has three buttons, one button per person, that the circuit tells them is if it's safe to ride the cycle or not. So they want to put an output, a little light that says that turns on when it's safe to ride this cycle. And the light, of course, will remain off if it's not safe to ride the cycle. All right, so let's get started. Hopefully you understand. It's just a really simple and kind of silly example, but the goal of today's lesson is to understand the process. And so that's why I chose an example that was quite simple. Okay, so keep in mind this little cycle and how there's only two seats and the person in the front has to steer and the person in the back has to pedal. So let's talk about the design process and what that means. Okay, so the logic design process has 5 steps. Step number 1 is to define the problem. Now, what do I mean by define the problem? So in this step, what you have to do is you have to list, actually no, not list them. You have to define. So you have to define all inputs and outputs, outputs, and the function of the output based on the inputs. So just the function. Okay, so let's do that for this first example. So in this first example, our inputs are going to be 3 switches, 1 for each person. So let's do that. So inputs are going to have, I'm going to call, for the first input, I'm going to call it A for Amy. I hope you noticed that I picked letters or names that just started with A, B, and C. So input A. Now, if an input is the signal coming into my circuit that is going to help me or help the circuit decide what to do. So the input is a switch, a sensor, any type of device that sends a signal in. Now, there's only 2 choices because it's binary. The signal coming in from input A, in this case like a push button, is either going to be a 0 or it's going to be a 1. Now, if A is sending a 0, that means Amy's not pressing the button. Amy is not pressing the button. Amy not pressing button. Okay. If A is sending a 1, that means Amy's pressing the button. Now, and that's going to be the same for the other 2 buttons. B is the same but for Ben, excuse me, and C is the same but for Charlie. So again, Charlie pressing button and Charlie not pressing button. You could also be like they're absent or present. Charlie not pressing the button. And wait, I put Charlie. That's supposed to be Ben. So this actually goes at the bottom. So this goes down here. Hey, I didn't catch that one. There we go. So now this one's Ben. Ben pressing button and Ben not pressing button. Okay, so those are my inputs. I've defined the inputs and that's all I have, just three. If I have, in this case, they all happen to be the same, but like in other examples, if you're talking about like a car door, for example, the sensor on the door would send a 0 or a 1 based if whatever you decide is shut or open. If you're talking about a motion sensor, a 1 or a 0 would tell you if there's motion or no motion, or pressure sensor or humidity sensors, depending on what you're working. So it's not always being pressed or not pressed. Sometimes it means something else. Now, for the output or outputs, in this case, I only have one output, and that's going to be a light. And it's not the same as the input. The input sends the information into the circuit. The output receives information from the circuit. So what do I want the light to do if it receives a 1? Well, I think it's most logical for most people to think that the light will be on if it receives a 1. So the light turns on, okay? And if the light receives a 0 or a low signal, the light stays off. Light is off. Okay, so that's so far. Remember, the problem is define all inputs, outputs, and the function. So let's define the function. What we want to do here is we want to say, we always start a sentence with the output. So in this case, the output is a light. So the light, and you just choose one or 0. It's most logical, again, to put 1. So the light will turn on if, and what you have to do is finish the sentence based on what's happening with the inputs. So for our example here, we have this bicycle, or not a bicycle, it's a tandem cycle. So we have this cycle that can only sit 2 people safely. If one person is there only pressing the button, then one person alone cannot ride the bike. And it requires 2 people because the front one is the one driving and the other one is pushing. So it has to be exactly 2 people, and 3 people, it is not safe, right? So our function, the way for this specific problem that I chose, the light will turn on if exactly 2 people press the button. Oh, press the button. All right, so there you go. We have completely defined all inputs, the outputs, what they mean, and how the output functions based on the inputs. All right, so now that we've done step 1, we are ready to move on to step 2. For step 2, I'm going to scroll this way. For step 2, what we're going to do is we're going to do the truth table. Okay. So again, this is a sure way. It's not necessarily the most efficient way to design a circuit, but it's definitely foolproof. Like if you follow it, you will get the circuit functioning properly. So the truth table, what do we do in step 2? In step 2, what we do is we list all the possible input combinations. So all possible input combinations in order. That's very important because if you put them out of order, it's not only difficult to find if you got all of them, but you may get them confused. So list all the possible combinations in order and the desired output for each. That's supposed to be one word. Output for each. All right, so based on that, again, let's put the both steps together for now. So based on that, we're going to build a list of all the possible inputs. So a truth table looks on the left side, we're going to put our inputs, and those are going to be, in this case, A, B, and C. And our outputs go on the right-hand side. And this is, I'm just going to write the whole word. That's the light. Okay. And so all the possible input combinations in order. So what I mean by that is don't start doing this. This is wrong. Like, oh, all on, all off, this one on, the second one on, the third one on. You may get all of them, but first of all, everyone's going to have a different order, and that's confusing. And second, more than likely, you will not get all of them. And later, if we haven't learned this already, you'll see that that's just a very specific pattern of counting in binary. So what you have to know is that the pattern always starts with all zeros. Okay, so, and it's going to end with all ones. But you need to know how many are there going to be in between. So I'm going to make a note right here. And that is the number of combinations. So, oh, my ink is kind of too thick here. So here we go. So the number of combinations is equal to 2 to the n, where n is the number of inputs, the number. So in this case, we have 3 inputs. So 2 to the third is 2 times 2 times 2. And that is 2 times 2 is 4 times 2 is 8. So I know I'm going to have 8 combinations total in this specific example on my truth table whenever I have 3 inputs. And this is the same for any circuit with 3 inputs. You're going to have 8 combinations. Okay, so I know it's going to be 8 combinations, but what order do I follow? Okay, so this is the order that you follow. Starting from the left and going, starting from the right and going left, this first column right here, you flip or toggle every time. So you toggle every time. So let's do that. It would be 0 and then 1 and then 0 and then 1. See how I'm doing it, flipping it every time until I have 8. So I know that's 1, 2, 3, 4, 5, 6, 7, 8. So I know there's 8. And I know I have to start with all zeros and end with all ones. The second column, starting from the right and moving left, this one right here, you would toggle every 2 times. That, and again, this is binary order, where it's like it's counting forward in binary. And again, if you haven't learned that lesson, it's a lesson that's coming up. So then this one is 2 zeros. Notice I start with 0, 0, that's 2 times 0, and then 1 2 times, and then 0 2 times, and then 1 2 times. And as you keep going, no matter how many inputs you have, you just keep following the powers of 2 or exponents of 2. So it would be 2 times 2. In this case, it would be 4. It's all about binary. Toggle every 4 times. And if I had a fourth column, it would be toggle every 8 times, and then every 16 times, etc., etc. I don't have a fourth column, so I'm not going to do that one, but that's how it would be. So this one would be 4 zeros and then 4 ones. And if I had a fourth column, it would be 8 zeros and then 8 ones. And then if I had a fifth column, it would be 16 zeros and 16 ones. So that's the pattern that you follow to fill all the possible combinations. So again, always start with all zeros, always end with all ones. Let's go look at the problem in its entirety again. So we've defined all the inputs and outputs. Now we have listed the left side of the truth table, but to figure out the right side of the truth table, what I have to do is I have to refer to the function so that then I fill the right-hand side of the truth table correctly. So this function is going to tell me what to put at the output, because I know that the light will turn on if exactly 2 people are pressing the button. So let's do that. For this example, the first row at this situation right here, no one is pressing the button because we said 0 means no one's pressing the button. Therefore, the output is going to be off because the light should not turn on because it's not safe to ride the bike. No one's there. The second row, only Charlie is pressing the button, and it is still not safe to ride the bike or the cycle because you need exactly 2 people. So the only time really when it's safe to ride the bike is when 2 of the inputs are 1 on the same combination. So here it'll be safe to ride the bike. Here it'll be safe to ride the bike as well as that combination. The rest of the combinations, that one, it's only one person, that's only one person, that's only Amy. And then the last combination is all 3 of them, and we said that is not safe to ride the bike. We are now done with step 2 of the design process, where we listed all the possible combinations in order following the instructions in red, and we have put the desired output for each following the function that we outlined in step 1. For step 3, what we have to do is the equation. So let's do step 3. What we have to do is the equation. I think a better word is the logic equation. So what are we going to do for the logic equation? What you're going to do is you're going to combine all the minterms, and I'll tell you what that is in a second. Combine all the minterms in a sum of products expression or equation. So there's 2 things to keep in mind. What is a minterm and what is this sum of products? Okay, so let's go back to step number 2 and review one little term. So every single time that, I'll highlight it in a different color. I'll do green. Every time the output is a 1, such as this one, or this one, or this one. In this case, we have 3 minterms. So you should know that wherever the output is a 1, I'm going to just point to them instead of circle them. Those are called minterms. Okay? So what we have to do is express an equation using only those. And what we're going to do is ensure that we include in your equation only where the output is 1. And by default, if we include only where the output is 1, the light will turn on when it should. And by leaving out the rest of them, so we leave out these completely, what's going to happen is that the light will remain off because we don't turn the light on for those. So again, we only focus on the minterms. We only focus where the output is 1. Now, I'm going to tell you 2 statements, and I think you're going to agree with me on the statement, and that has to do with how to write, whether it's and or. So let's focus only on this situation happening right here. So which statement sounds better? At that situation, this is statement 1. For this situation, the light is on because Amy is not pressing the button, and at the same time as Ben pressing the button, and as Charlie pressing the button. Does this second statement sound better? At this situation that I circled in blue, the light is on because Amy is not pressing the button, or Ben is pressing the button, or Charlie's pressing the button. I think you will agree that the correct wording will be and, because that situation is happening at the same time. And all the 3 inputs have to be that particular state for the output to be that, what's happening. So what we're going to do is, for this situation, we're going to say that situation is expressed as Amy is not pressing the button, Ben is pressing the button, and Charlie is pressing the button. So I wrote it in blue for that situation only. For the next situation, I'll use a different color to separate them a little bit. So for the next situation, that is a 1, the next minterm, it's this one. you'll agree that it's the same thing as the blue, but with a different person being not pressing the button. So what makes that situation true is that Amy is pressing the button, so Amy's a 1. Ben is not pressing the button. So notice that I put a bar over when the answer or the input is 0, because what's going to happen is the input is 0, and if we want to force it to be a 1 at the output of the AND, we have to invert the logic to force it to be a 1. So just as a rule, put a bar. Let me make a note of that one. I'll put it in, I'll put it in red. So for the terms, place a bar or an inverter over the term, over the letter, over the input that's a 0, yeah. Inputs that are 0. And it doesn't have to be only one. In this situation, there's only one, but sometimes there's multiple. So that's a note to say about this one, and what I'm about to do with this one. So I haven't finished the green one, by the way. So A is on, B is off, so we put a bar over it, and C is on, so we just leave it like that. Let's see, what other color can I use? I guess I'll use purple. So the third min term that has a 1 at the output, we would say that situation's happening because Amy is pressing the button, Ben is pressing the button, and Charlie is not pressing the button. So those are our min terms. There's 3. And in blue, green, and purple text, that's how we express each min term. Now, lastly, the equation is going to be the following. I'm going to make 2 statements again, and you'll see that the second one is the correct one. But let me say them so that you understand. So this is the statement that I'm going to say. The light will turn on if this situation is happening, and at the same time as this situation is happening, and at the same time as the last situation is happening. You can see that that doesn't sound right because there's no way that the green and the blue and the purple situation are happening at the same time because each input is different for each one. I think you'll agree that the second statement sounds better. The light turns on if this situation's happen, or this situation is happening, or if that situation is happening. So the correct way to group those terms is with OR logic. And that leads us to the answer for the equation. So the light, I'm writing with the wrong thing here. The light will turn on, or it's going to be 1, if the first situation is true, which is the blue, which is not A, Amy's not pressing the button, and Ben and Charlie are. Or we write the addition symbol. The second situation is happening, which is Amy's pressing the button, Ben is not pressing the button, and Charlie's pressing the button. Or if the last situation is happening, where it's Amy's pressing the button, Ben is pressing the button, and Charlie's not pressing the button. As you can see, our equation is in a way that looks like things are being ANDed first, and then they're being ORed. That is what we call sum of products. It's the addition of things we've multiplied. So that's a sum of products form. And so now we have captured all the times that the light should be on. So again, for our process, we've defined all the inputs and outputs, how it's supposed to work. We listed every single combination in step 2. And in step 3, we've captured for all the combinations, which ones of those should we focus on turning the light on. And we have listed them in a sum of products form. Okay, and those combinations where the output is a 1 is called a min term. The next step in the design process is now step number 4, which is logic implementation. Here we go. In logic implementation, what you're going to do is basically uh, build a circuit, schematic, and you could do this using a software like Multisim, or you can sketch it by hand if you don't have it. So build the circuit schematic using AOI logic gates. You know what? I should emphasize at this point, I'm going to put this in parentheses because later we're actually going to use other ones. So build the circuit schematic using logic gates. I'm going to put using logic gates. And for now, we only have AOI 2 input gates. But later in other lessons, we may be able to use other ones. So for right now, we're going to leave it like this. Okay, so I'm going to sketch this one here, and I could show you how to do it in Multisim as well. But for now, I'm going to put a battery here, and depending on the software that you're using, I'm going to use 5-volt battery because my AOI logics work with 5 volts. And what I'm going to do is I'm going to put the positive side of my battery, this is right there. I'm going to put a wire and end it with a junction right there so that I have a wire. The negative side, I'm going to put it like that. And I'm also going to connect the negative side to ground. And so I know that this represents my 0 and this represents my 1 connection. Next, I'm going to put my switches. Now, typically we use a single pole double throw switch going from left to right, but I think it's going to be better in this example if we connect the switches going downwards like this. So the 2 inputs are on the top and the outputs at the bottom. So this switch represents A, and I'm color coding just so that you can follow along. But for me, to the left, if the little lever that's there is to the left, it's going to be sending a 0. And if it's to the right, it's going to be sending a 1 out of the bottom. So this, I'm just going to draw a wire. Oh, that's kind of crooked. I'm going to draw a wire going down. I'm going to put a junction there so it ends and it stays there. So that anything I connect to this wire right here is going to be the same as A. So that's why I choose to do it like that. So it's not going to get so messy and tangled up because we have wires going everywhere. So that's a really good tip, I think, that I've gotten over the years to draw the circuits. This next switch that I placed is going to represent B. And again, I draw a wire going down and end it like that. And last but not least, we have a third switch for Charlie. And I connect the left side of it to 0 and the right to 1. So my switches are ready, and again, these is where you would toggle them back and forth if you have software simulation, software simulator, and that's prefer. Okay, so how do I go about building this one? I'm going to follow the color coding that I put over here on my equation on MinTerm. So this first one, I'm going to make it or underscore it as blue. The second one, I'm going to underscore it as, oh, that's not the same green. I think it's this one. So I'm going to underscore it as green. And the last one is going to be this light purple. So I want to point out that when you build the circuit or you implement the logic, you need to follow order of operations. Okay, so I should add that to my circuit using logic gates and following order of operations. Now, order of operations, I'm going to put it over here on the left because I don't fit it over there. But it's the same thing as in algebra, which is the PEMDAS, the PEMDAS. So parentheses are first. So order of operations, I'm going to list it here. So the order of operations is parentheses first, same as in algebra. The next one would be exponent in algebra, but here we don't have exponents. We have the bars or the inverters on top. So we put inverters, I can't spell, inverter, um, inverters. Then after the inverters would be, please excuse my, there would be multiplication. So multiplication is for us AND logic. After AND logic is division, but we don't have division, so we just go to the next one, which is OR logic, and we don't have subtraction. So this is the order of operations that we must keep in mind when building our circuit. So as you can see on this example, I cannot just go build my equation going from left to right. That is not correct. I have to first build each one here, here, and here, and then I can combine them. So let's start with the one highlighted in blue, and I'll use blue to build it on the equation. So I'm going to focus on that one. Okay. So as you can see, I'm ANDing A and B and C, but A has an inverter, and as you can see, the inverter has a precedence over the AND. So what I'm going to do is I'm going to take A, B, and C. I'm going to AND them all together. But before I AND them, I have to take A and I have to invert it. So I'm actually going to erase a little bit right there, put the inverter right there. Now I can AND those three signals. I could use a triple AND gate, but again, for this first one, we're going to try to learn to build them with using two inputs. So what you do is you first AND the two that are available, and then the result of that you AND with the second one, and that'll give you the result. Let me write in red or highlight them in orange, I guess, the signal names that are going into my logic gate. So A is going into the signal right there from the switch A. The opposite of A is coming out of that inverter. In the second wire, we have B going into the AND gate. The result of that first AND gate is not A, or the opposite of A, ANDed with B. In the third wire, we have C going in, and the result at the second AND gate is the result of ANDing not A, B, and C. Now, I would like you to think about this and realize that the only way this circuit right here is going to be a 1, the only time the circuit's going to be a 1 is when both of these inputs are a 1. Further back, the input of the first AND gate, in order to give an output at 1, must also be both 1s, because AND gates need all inputs to be 1. And going back even further, in order for the opposite of A to be 1, A must be a 0, because the opposite of 0 is 1. So following that logic, the only way I'm going to have a 1 at the output is when A is 0, B is 1, and C is 1. Therefore, going back over here, notice the first term right here. That's when it's A is 0, B is 1, and C is 1. So the only circuit combination that's going to make my output be 1 is the first minterm for this circuit in blue. Okay, so that's super important to understand. I'm going to erase that for now and continue with the next one. Now let's continue with the one in green. Actually, it doesn't matter. I could leave that as 0, 1, 1. This becomes a 1, and that's a 1. Okay, so let's do the green circuit, which is right there. So for the second little term right there, I need to AND them all, but before I AND them, again, following order of operations, I need to invert B. So I'm going to take A, B, and C, and I'm going to AND them, but I'm going to take an inverter, and I'm going to invert B right there. And then I just AND all three. Again, I can just AND the first two, and then get the result and AND the third one. Let's see, this is what's going into this circuit. We have A going into the top, B going into the inverter, and then the opposite of B comes out. out of the first AND gate, we get A with the opposite of B ANDed together. C goes into the bottom wire, and the result of this one is A and not B and C. Let's do the same exercise as we did with the blue circuit. And what is the only combination that's going to result at a 1 at the output? Well, in order to have a 1 at the output of the AND, these two circuit signals should be a 1. Further back on that AND gate, in order for the output of that AND gate to be a 1, both A and the opposite of B must be a 1. And lastly, in order for the opposite of B to be a 1, B must be a 0. So in order to have a 1 right there, we're going to have a 1 there at A, a 0 at B, and a 1 at C, as compared to the one above where it has to be 0, 1, 1 for A, 0, B, 1, and C, 1. So my green little circuit section will only allow the second minterm highlighted in green in my truth table. It will only allow that combination to put a 1 at the output of that green AND gate output. Okay, now let's continue with the last part of the equation before we OR them all together, and that's in purple. Now, I just realized that I didn't make my wires long enough, so I'm going to extend them a little bit. Okay. So here they are. So now let's build the circuit. So for this one, we AND them all, but before ANDing, I have to invert C. So I'm going to take A, B, and C. But again, I have to invert C before ANDing them. And then I AND them all together. I take like that. So again, I have A going in, B going in, I get A and B. C comes in, but the opposite of C comes out. And so the result here is AB and the opposite of C, or not C. And I will do it one more time to make it super obvious. The only thing that's going to make the output of that purple circuit be a 1 is when both of these inputs are 1, meaning that these inputs are 1, and the opposite of C is a 1, so C must be a 0. So the only input that's going to make the output of that purple circuit be a 1 is 1, 1, 0, which is the third minterm right there on my equation. So I hope you see that we are building only the circuits that are going to produce a 1 for those minterms. Again, we only focus on the 1s. And so we're almost done. We just need to make sure that all those can produce a 1 at the output. So what we have to do is combine them all using OR logic, because that is what is in between each of the terms. So I guess I'll use orange here. Oh. So I'm going to say this logic, if there's a 1 there, or if there's a 1 there, I'm going to have an output right there. And so my equation would be the first output or the second situation can put a 1 right there. And then I take this signal and I combine it with the last one, and that'll give me the total equation, which is not ABC, or A not BC, or AB not C. And then the output, I just connect to whatever my output is. I guess I could put an LED. I'm going to use a little lamp. I'm going to use like a 5-volt lamp. Actually, the one that is on Multisim Live is anything above 2.5 volts. We'll turn it on. And so I don't even need a resistor on this one. I could put an LED, but I need to put a resistor if I don't want to burn it out. And then I can connect it all the way back to ground over here. Or I could just put another ground, which is the same thing right there. So now, again, let's recap, and we're almost done. The step 1 is to define all the inputs and outputs. Step 2 is to list all the possible input combinations and when I want the output to turn on. And step 3 is to figure out which of the outputs turn on the light, which of the combinations turn on the light, and those are called minterms, and we write them in a sum of products form. And then we build the equation following that sum of products form. If we had had 4 minterms, you would have 4 terms, in this case 4 different colors. And then after they're all done, we OR them to each other and connect them to the output. Okay. The last step, and we are done, is step number 5, which is test the circuit. So I think that one is self-explanatory, but I want to highlight one thing that some kids forget. So what you have to do for this one is to build a circuit in software or breadboard, right? Breadboard. And toggle the switches, toggle the input switches to match all the truth table combinations. That's super important because some kids just check, oh, did it turn on when it should? But if you make an error, what you may be doing is turning it on when it should not turn on. So you want to make sure that that you toggle all of them to match the truth table and verify that the output is correct. Verify that the output is correct. Again, that one I would only be able to show you if I had the circuit built, which I don't in this case, but that's the process. So you would, and again, if you did it right, you would only get those 3 combinations to show the output. All right, so there you go. In the next lesson, we're going to be looking at how to implement the circuit in Multisim, but you've done it before, so it should not be so difficult. But that's the design process, and don't skip on any of the steps because otherwise you'll miss a beat. And again, there's other ways to implement or build the circuit, but this is the sure way to do it, that if you follow it exactly, you will always get a functioning circuit. It's not necessarily the most efficient. Later, we'll figure out how to make it more efficient. But for now, this is the best bet. All right. I hope you understood this. And all right. Ta-da for now. Bye-bye.